Okay, lesson 6.6. This one is on probability and odds. There's a lot of information that can be discussed with the idea of probability. You can take classes in college that the entire course is nothing but on the topic of probability. We're going to try to hit the highlights. We're going to try to condense it and get you all the essentials here so that you can do the basic probability problems. Now let's take a hypothetical. Consider, you're playing a board game with a friend and it's your turn to move. You roll a die to determine how many spaces you move. You notice that if you roll a 5, you'll win the game. How likely are you to roll a 5 and win? Well, with that in mind, let's go over some vocabulary. Rolling the die is an example of an experiment. In probability, they talk about experiments. It could be picking a card from a deck of cards. It could be rolling a die. It could be flipping a coin. Those are all experiments, not experiment like you would have in a chemistry class. Now, the next one. The possible results of an experiment are outcomes. And when you roll a die, the outcomes are you get a 1, a 2, a 3, a 4, a 5, and or a 6. So like when you flip a coin, you could get heads or tails. Those are the outcomes, the possible outcomes. All right, now, third one, an event. An event is an outcome or a collection of outcomes. So in the game we're playing, we're trying to roll a 5. Rolling the 5 is an event. Okay, that's an example of an event. Or if you're flipping a coin and you want it to come up heads, you call it heads. The heads would be the example of the event that we're trying to have. It's an outcome, or it can be more than one outcome, a collection of them. Now, the favorable outcome would be, as the name indicates, the one that you want to have happen. We want the 5 to show up, so that would be our favorable outcome. Out of the 6 possible outcomes of rolling a die, we want a 5. If we're flipping a coin and we want it to come up heads, the favorable outcome would be that it comes up heads. All right, now with all that vocabulary, let's actually define what probability is. The probability of an event occurring is a measure of how likely, or of the likelihood that the event will occur. You see this all the time on the news when the weatherman's talking about the likelihood that it rains the next day. You know, there's a 10% chance of rain, there's a 90% chance of rain. What he's doing essentially is finding the probability that rain is going to occur the next day. It is a measure of the likelihood that the event will occur. To determine the probability of an event, of something happening, what we do is we use this little formula right here, where all the outcomes are equally likely, and the probability of the event is the number of favorable outcomes over the number of possible, the total possible outcomes. So it's favorable over total. Think of it like that. So let's go back to the problem with the board game. You want to roll a 5 and win the game. The probability of getting a 5, well, when you roll a die, there's only one 5, that's one side, that's a 5. And that's out of the total number possible, that's out of 6. So the probability turns out to be 1/6. The next example is still with a die, only they call it a number cube sometimes. Suppose you roll a number cube, what's the probability that you roll an odd number? Well, the probability of getting an odd number, there are 3 odd numbers, the 1, the 3, and the 5, and that again is still out of 6, total possible. So you get 3/6, which simplifies to a half. So the probability would be 1/2. Now notice here that I'm writing my probabilities as fractions because of this way this is set up. Probabilities are usually written as fractions. They can be written as decimals or even percents. Like I said with the weather forecaster, a 10% chance of rain the next day. What we can do is we can typically write it as a fraction so that we can simplify these and make this a little bit easier. Now, next thing up, it says, suppose you pick a card from a standard deck of cards. What is the probability that you pick a king? Well, you would have to know that there are 52 cards in a standard deck of cards, not counting the jokers, and you would also have to know that there are 4 kings. The probability of getting a king would be 4 out of the 52 possible cards. Now this one simplifies. I can divide top and bottom by 4, and I get 1/13. Okay? Then it says here, this is more of a summary here. Make sure that you understand this good. Understand these well. There are examples of theoretical probability. These are examples of what we call theoretical probability. Now, you know what a theory is. It's based on knowing that all the equally likely outcomes of the event. When we roll a die, we know that it's the same probability to get a 1 as it is to get a 2, as it is to get a 3, as it is to get a 4, as it is to get a 5, as it is to get a 6. When we pick a card from a deck of cards, any of the cards are equally likely to come up, as long as we pick one randomly without looking. Now, probability is going to be a number. Notice these numbers here. These numbers are going to be between 0 and 1 inclusive. And that makes sense because the number of favorable outcomes can't be more than the number of total possible outcomes. The most that could happen is if the number of favorable outcomes equaled the number of possible outcomes. And that's when you have probability 1. And then down here, probability 0. Probability 0 would be if there are no favorable outcomes, if you have a 0 in the numerator. So that's impossible. When they talk about something having probability 0, that means that event is impossible to happen. If they talk about the probability of an event being 1, that means that event is certain to happen. Besides theoretical probability, we also want to consider a type of probability that's called experimental probability. Experimental probability is not based on necessarily equally likely things to occur. It's based on repeated trials of an experiment. I mean, when you're a little child and you touch a hot stove, you burn your fingertip. And if you do it again, you burn your fingertip. And you burn it. That's a trial. Each time you do it, you repeat the trial, and you have the same results. Each trial in which the event occurs is a success. See, sometimes a child will touch a stove, he'll burn his fingertip. Sometimes the stove isn't on, he touches the stove, and he doesn't burn his fingertip. But those are all trials. When you don't burn your fingertip, we'll call that one the success. That type of a trial would be considered an success for that event. The probability, the experimental probability, is the number of successes to the number of trials. So that's a little bit like the theoretical probability, which was favorable outcomes over total outcomes. This is the number of successes based on the number of trials. Consider a couple of examples here. Of the first 70 people at a theme park, 18 visitors agreed to participate in a survey. Find the experimental probability that a theme park visitor will participate in the survey. So the probability that they will participate based on this information would be the favorable or successful trials. That would be the 18 people that said, yeah, I'll do it, out of the total number of people that they asked, and that would be out of 70. 18 over 70. Now that one will simplify because you can divide top and bottom by 2, and this simplifies to 9 over 35. If you get a phone call late at night and it's somebody trying to sell you something and you hang up on them, but you keep getting phone calls, it's because some people, when they call, will buy whatever is being sold. And so based on that, they'll continue to call people hoping to find more sales. So if nobody bought anything that was based on a late call like that, then they eventually would stop because it wouldn't be feasible to pay somebody money to make phone calls if nobody's bringing any money in from sales. All right, the next one up. Now this is going to involve experimental probability, but it's an expectation problem, and you will see this a lot, including proficiency. Last year, Sarah planted 12 tulip bulbs, but only 10 of them bloomed. This year, she intends to plant 60 tulip bulbs. How many should Sarah expect to bloom? Now, this is going to be based on last year's trials and successes. Remember, she planted 12 tulip bulbs. That would be 12 trials. 10 of them bloomed, so that would be the successes. So the probability, the experimental probability, would be 10 out of 12, or 5 out of 6 if I simplify it. Now here's where we use a proportion to help us find the expectation that this year how many should bloom. I'm going to take the experimental probability from last year's plants, and I'm going to set this up. She's going to plant 60. That would be the total number of trials here. That's my denominator. I'm going to put a 60 down here. X will be my numerator, how many we expect to bloom. So this is the successes, those that bloom to the total number of trials, successes to total number of trials. So now you can see this one coming. I'm going to cross multiply. I get 300 equals 6x. I'm going to divide by 6, and I'm going to get x is equal to 50. She should expect 50 to bloom. So it's based on that probability from the previous year. Now, we're going to talk about something that's similar to probability, but it's not exactly the same, but you're going to see how easy they are to compare the two. When all outcomes of an experiment are equally likely, this is the same as theoretical probability, the ratio of the number of favorable to the number of unfavorable is called the odds in favor. See, probability, theoretical probability, is favorable to total. Odds would be favorable to unfavorable. You have odds in favor, favorable to unfavorable. You have odds against, unfavorable to favorable. So it's quite a bit like theoretical probability. You just have to remember the denominator is not going to be the total. Okay? So what we're going to do is a couple of examples of this. Now remember that probability is a number that describes the likelihood of something to occur, and it's between 0 and 1 inclusive. You know, the closer it is to 1, the more likely something is to happen. The closer it is to 0, the less likely it is to happen. But with odds, the actual ratio that you can write might be more than 1. So remember, it's not exactly the same rules. Okay, let's try this example. Suppose you randomly choose one letter from A through I. So let's see, A, B, C, D, E, F, G, H, I. There are 9 letters from A through I. What are the odds in favor of choosing a vowel? Well, let's see, there's A, E, and I. So 3 out of the 9 are vowels, the other 6 are consonants. So the odds in favor of choosing a vowel, well, that would be 3 favorable to 6 that are unfavorable. 3 to 6, which would be 1 to 2, or 1/2. 1 to 2 is probably a better way to state that. Then it says, what are the odds against choosing a vowel? Now this time it's against choosing a vowel, so it's the other way around. There are 6 that are unfavorable, and there are 3 that are. So in this case, it's 6 to 3 or 2 to 1. Now I'm going to leave it as 2 to 1. I'm not going to write that as 2 because, remember, odds are a ratio, and we want to write it as a fraction if at all possible. Okay? Note the difference there. If I had asked what's the probability of choosing a vowel, it would have been 3 to 9, or 3 out of 9, or 1/3. So there's definitely some tie-ins here, but as you can also see, the answer to B is greater than 1. Remember, probability is between 0 and 1 inclusive. Now, here I'm going to do the same experiment, but I'm going to ask a probability question and an odds question. Let's see, suppose you randomly choose a number between 1 and 9 inclusive. Now that means it includes the 1 and includes the 9, or the 19, excuse me, 1 and 19 inclusive. Between 1 and 19 inclusive includes the 1 and includes the 19. What is the probability of choosing an even number? Well, between 1 and 19 inclusive, you have 2, 4, 6, 8, 10, 12, 14, 16, and 18 are all even numbers. That's 9 numbers. 9 are even, 19 possible. So it's 9/19, which does not simplify. Now let's change this problem. Let's do an odds problem based on the same experiment. It says, what are the odds against choosing a multiple of 3? Where your multiples of 3 are 3, 6, 9, 12, 15, and 18. That's 6 multiples of 3. We want the odds against choosing a multiple of 3. So if there are 6 that are multiples of 3, 19 minus 6, there are 13 that are not. So the odds against choosing a multiple of 3 would be 13 to 6. And again, you can see that's bigger than 1. And I'm not going to change that to a mixed number. I'm going to leave it as a fraction. All right, so you're getting just a glimpse of the wonderful world of probability. It is an extensive field, but if you get the basics down, that'll help you not only in this chapter or in this unit, but it will also help you in proficiency problems. So remember, practice, practice, practice.